হ্যালো সন্দীপ, শুরু করতে পারে।
Very good afternoon to everyone. I am Somjit Roy. On behalf of the entire team of Probability Space, I welcome you all to our first webinar. So it's an honor to us. It's a great honor for us to have Professor Arnab Chakraborty from Indian Statistical Institute, Kolkata. It goes without saying that Professor Chakraborty needs no separate introduction, as we being the community of students related to either statistics or mathematics, we are quite familiar with his books, which had a profound impact on most of us. And it would be unjust for me to not mention his blogs, as to some extent it motivated in the inception of this club. Today, he will be enlightening us on one of the most perplexing paradoxes on mathematics, which is the Banach-Tarski paradox, which will to some extent reveal why the axiom of countable additivity is so crucial in defining probability measure. And we will get to know that after all, why from a theorem it got converted to a paradox. So let's hear it from sir. So you can start.
Okay, thank you very much. I feel very happy and honored to be the first speaker in your webinar. Now, the topic that I am going to talk on is indeed very befitting because this gives rise to the very concept of probability space. So probability space or a measure space, that idea starts from this particular topic. So whatever we are going to do here, that is a paradox. Now let me just start sharing so that you stop seeing my face and start seeing something more useful. And what is that useful thing? Let me see. Yeah, here it is. Good. So this is the Banach-Tarski paradox, or more appropriately, it should be called the Banach-Tarski theorem. Now, in a nutshell, it is just this, that you can take a pea that's just a vegetable pea, that small green thing, and you can chop it up into finitely many parts and reassemble to produce something as big as the sun. So sometimes the same paradox is couched as the pea and sun paradox. Now, in order to understand this, the proof, which is not exactly short, it has lots of brilliant ideas, but it uses nothing other than basic arguments involving countability. That is countable, uncountable, and things like that. Nothing more advanced than that. So let me first make sure that we all understand what is meant by counting. Now you might very naturally feel humiliated that I am saying whether you know counting or not, but just get started in a fun way. So the picture that you are seeing is a puzzle which was introduced by a famous American puzzlist called Sam Lloyd. He called it Get Off the Earth puzzle. Now it consists of a piece of cardboard, or rather two pieces of cardboard, one fixed inside the other. Here you can see a circular thing, that's the globe kind of. And, and this thing can rotate inside the outer thing. So I will ask you this question. How many people do you see around the periphery of the globe? So let's see whether we can all count. Can anyone count for me? 1, 2. So how many people are there?
12, I guess. 12.
Yeah?
12.
There are 12. Okay. So everyone should think that there are 12, right? Now let me see whether you really understand counting or not. Now look carefully. What I am going to do is I am going to turn that inner disk. Look carefully. I am just rotating it. I am not hiding anything. I am not bringing anything from anywhere else. That's it. I have not hidden anything. I have not added anything else. So can anyone please count once again how many people there are?
Thirty.
Now the number is 30. So this shows that you do not
One
know how
more.
to count,
Yes.
right? You do not know how to count. How can I talk to you about Banach-Tarski paradox? Well, the thing that we are going to talk about is a sophisticated version of a very similar idea, except that it is not really cheating. In this case, we are actually cheating. If you look very carefully, you will be able to see how this paradox can be resolved. So I am leaving that to you. If you want, I can just go back and show you the thing. I started with this and I went to this. How come the number went up? And it is not at all difficult to construct this puzzle yourself. So you can think about that. But the main theme of this puzzle, the reason that it is puzzling is because our everyday experience says that certain transformations are not expected to change certain things. Certain things will remain invariant. For example, if I take an object and just rotate it, do we expect that its volume will change? No. If I translate it, the so-called rigid body transformations, then they should not change length, they should not change area or volume. That's our everyday experience. And so when I just rotated that one disk inside another, I would not expect that the number of people should just change. They might get reassembled, but that should not really change. And when that happens, that's surprising. Now, what we are going to do is exactly the same thing. So now I am in a position to tell you what this Banach-Tarski theorem is. I call it a theorem because it has a perfectly rigorous proof, no cheating anywhere. And the theorem says it is possible to split a solid ball. So I start with a solid ball, a ball in 3D. So it can be generalized to higher dimension also. So it's a ball together with the surface and at the same time its interior into finitely many pieces. No infinity, no countable infinite, uncountable infinite, finitely many pieces. The pieces are non-overlapping. And then I shall just rotate them. That's it. I'll merely rotate them, no other transformation, and refit them together, and they will fit perfectly without any overlap to form two solid balls exactly identical to the original ball. So I take one ball, split it up into finitely many parts, reassemble, and get two balls out of that one ball. So basically that proves 1 is equal to 2, and you repeat 2 is equal to 4, and every number is equal to every other number, and chaos. Surprising fact, it is a theorem, and this talk is devoted to a perfectly rigorous proof of that theorem. Naturally, such a theorem has tremendous repercussion in various branches of mathematics, not the least of which is measure theory. It sort of started the entire thing of measure theory, of which probability is one of the most important branches. Okay, so let me start with the basic idea using some very simple, hands-on kind of examples. And this will also build up certain tricks that we will put together to create the proof. So here is step number 1. I start with a circle. Like you can see the circle with just a single point missing. I have shown you that single point. Now, I have of course shown a little part of arc missing because I cannot draw a single point. You understand that's just a single point, not a part of arc. My question is, can you break it up into two non-overlapping parts? Rotate one of the parts and refit to get a complete circle. So remember, we all know that dropping one point still keeps it uncountably infinite. So I can get a bijection between the entire circle and that circle with one point missing. That we all know. That's pretty easy. My contention is something stronger. I want to break it up into just two parts, and the only transformation that I shall allow is mere rotation. And still, that hole will go away. There will be no overlap anywhere. The same thing together with the whole. So as if the whole is just not there. So let me show you how it is to be done. This is not at all difficult. You will get it if you think about it for the 15 minutes. So I will show you the trick. The trick goes like this. First, consider the radius through that particular hole. And if I turn that by, say, 1 radian, you will get to a new point. You will get to that red point. I have turned it by 1 radian. Okay, turn it by 1 more radian. So you get 2 radians. You get another red point. Go on, go on, go on, go on. And when you go on, you will overshoot the original gap. Notice that you will never come to that original gap, because had that been the case, 2 pi would have been an integer. Suppose after moving after 5 steps, you come exactly to the same point, then 2 pi will be just 5 radians. 2 pi radian will be 5 radian. That is not true. Now, if I continue going like this, all the points that you will get like this will be distinct, because if at some point you come back to some earlier point, what will that mean? Suppose I say that after 10 rounds, I come back to the same point. So that means after 10 steps, say for example, after 100 steps, you come back to the same point. So that means 100 radian is actually an integer multiple of 2 pi, which means 2 pi is a rational number. We know that is not the case. So all the red points that you will get, if you go on and on and on and on, that will be an infinite set. All the points will be distinct. And of course, that will be, you can kind of feel that that will be actually a dense set. So we do not need the dense property here, but it will be a dense set in that surface. Okay, now what I shall do is I shall do the other way around. I shall again start with the same radius, but now I will rotate it in the clockwise direction by 1 radian and get this green point. So whether you consider the red points or the green points, they will be all distinct, and together they will give you lots of points, a countable dense subset of the arc of the surface. Well, that's it. Now I said I have to split it up into 2 non-overlapping parts, and this is how I do it. First, I will introduce a little mathematical notation. I will call this transformation of rotation by 1 radian rho. So I initially had rho to the power 0, which is the original gap. Rho to the power 1 gives me the first red dot, rho square, the second red dot, so on. And rho to the power -1, rho to the power -2, they will give me the green dot. So I get these points. Just a mathematical notation of whatever I have done. So now I get 3 types of things that are shown in the picture as green points, all the rho to the power -n things, all the red points that are rho to the power n kind of things. I am applying them on the gap point, and the rest, the thing that shows up as black. These are, of course, disjoint, because no 2 such points can really match, because 2 pi is irrational. Okay, I said that you have to split it into 2 parts. Well, what you do is you can take any of the first 2 parts. Suppose I take only the first part and put the second and the third part in one lot and keep them fixed. What I do is I just rotate the first part by 1 radian counterclockwise. Okay, so I just rotate it counterclockwise by 1 radian. Now, when I do this, I just rotate it counterclockwise by 1 radian. What happens is that rho to the power -1, that green point, comes to the gap. I think I have some way by which I can bring that pointer. I do not know how to bring that pointer. When I practiced, I had that pointer somewhere. Okay, anyway. So you can all see it, right? No problem with that, right? You can see it.
Absolutely.
Yes, sir.
Okay, okay.
Absolutely.
Yeah. So it is just somehow that my pointer thing which was supposed to be here has vanished anyway. Okay, so this rho to the power minus 1 now goes to the gap, and rho to the power minus 2 comes to the place of rho to the power minus 1. The minus 3 thing comes to minus 2, minus 4 comes to minus 3, and since it goes all the way up to minus infinity, it will never lack supply of points. So you have just covered that blank point by the minus 1 point. The minus 1 gets covered by minus 2 point. Minus 2 gets covered by minus 3 points. So everything gets covered, and the gap just goes up. So I have achieved exactly what I wanted to achieve. I have split my circle into two parts, two disjoint parts. One is that rho to the power minus n things, and whatever is left, they are by definition disjoint. I have done nothing but rotating the first part by 1 radian counterclockwise, and lo and behold, I have got rid of that gap. So this thing is going to be an important step in our proof. I shall call it the circle trick. And the circle trick simply says, if you have a wheel with a puncture, you can always rectify it out of nothing. You just split it up into two parts, give a slight rotation, and it is rectified. And now this reminds me of a little story that those of you who are Bengali here will possibly recognize it. The story is by Shivram Chakraborty. And the story went like this, that one day Shivram just borrowed some money from one guy. Now he did not have any money to repay it back. So what he did was that he just borrowed the same amount of money from a second guy, and with that he paid back the first guy. And then after some time he borrowed the same amount of money from the first guy, repaid it back to the second guy, and he went on doing this all the way. So the very first money that he borrowed from the first guy, so Shivram was just free to use it as he liked. Now, of course, in practice, that will not work because you cannot go on doing this an infinite number of steps. Someday or other, you have to come to the last transaction, and then you will see that you have some money unaccounted for. But here we are working with infinity, and that's fun. So we have to never account for what happens at the end because there is no end. Okay, so that's the circle trick. That's not very great. That is nothing that profound, kind of fun. Now suppose I give you more gaps. So again, the same circle, but this time I give you two gaps. And now I know your trick. So what I do is I give you two gaps that are situated exactly 1 radian apart. So I give you a gap at rho to the power minus 1. So the problem is this. Once you put that, how are you going to fill up that top gap? Because the point that was supposed to fill up that gap is not there itself, because this gap will go onto that gap. So I want a point to fill up the gap. I cannot use one gap to fill up another gap. But that is actually not a problem at all, because there was nothing profound about choosing 1 radian. I can just do something else. So just choose an angle that does not take one gap to another, and it must be an irrational multiple of pi. As long as it is an irrational multiple of pi, you know that all the points will be distinct. You will never trade on your own tail. And just take something. Say if you are given this, I will take, say, pi by root 2. That will do. Now, if you can do that, then obviously I can work with any finite number of them. So I will just see all the differences, angular differences between the gaps, and I will just avoid them because there are uncountably infinitely many things that I can choose from. Take pi, multiply that by any irrational number. There are uncountably infinitely many things there. So if you have to avoid finitely many, you can always do that. For that matter, why stop at finite? You can even work with countable number of gaps. Because as I said, we have an uncountably infinite supply of rationals. If you have to avoid countably many gaps, well, you can always find still an uncountable number of irrational multiples of pi to work with. So that is a pretty powerful technique. So if you have a wheel where you have a countable number of gaps, suppose all the rational points are missing, even then, just by splitting it up into two parts and rotating one, you can rectify all the gaps simultaneously. So if you own a bicycle, you might consider this the next time your tire springs a puncture. Okay, but we said we are working with a solid ball. Now we are working with a one-dimensional stuff. Now I will work with something which has got area. But the idea is pretty similar. Suppose I work with this annulus. Same thing. Earlier, I was removing only points along the circumference. Now I will cut slits. Just the slits that I am showing. So I will basically cut the slits. So I will basically just cut the slits. And whatever I said about the points at the circumference, I will say the same thing about the slits. So I will rotate one slit from another, etc., etc. So absolutely nothing new. Okay, now let me ask you a puzzle so that you know how to work with if I give you slits like this. Now I will ask you to do the other extreme. No slit. I will remove the very center. So here you have the punctured disc. It is in R2, just the disc, interior along with the boundary, I do not mind, but the very center is missing. That point is missing. I ask you to do the same thing. You have to split the punctured disc into two parts. When I say two parts, no overlap, nothing. There should be just a partition of this into two parts. Rotate only one of them to hide this hole. And even after rotation, the thing must fit perfectly. No overlap or anything, no gap, no overlap. If I ask you to do this, you might first start thinking how to do that, but after thinking for possibly 1 minute, since it's not an offline lecture, so I cannot really pause and just go about poking people around. So I will just give you the answer. And the answer is the following. You just draw a circle like this. Just draw a circle that passes through that gap. Now forget about the rest of the green disc. Focus your attention on that circle. That circle is exactly the type of thing that we discussed so far. So it's a circle with a gap. So all that you do is you take all those points, you just move the gaps along that small circle. So you get that rho to the power minus n kind of things. Rotate them by 1 radian. You cover that hole and leave all the remaining part of the green disc just untouched. So whenever you see any hole anywhere, you just imagine a circle containing that hole in its origin, in its circumference, and apply that circle trick. So the fact that we are working with a circle is not important. The important thing is that if you have a hole, you can always use this trick. You introduce the circle at your own convenience. And the same argument holds if you have finitely many, countably many holes anywhere. So next time you have a leaky roof, you might try that. Now let's come to puzzle 2. So now we are heading towards a three-dimensional thing, but still it is not really three-dimensional. It is a sphere, so just the scheme of the thing. So I consider a sphere with holes. So the inside is empty, it's hollow. And it has got holes, countably many holes. And my puzzle asks you to do the same thing. You have to split it into two parts. Rotate one and refit such that all the holes just vanish. Same conditions, no overlap either before or after the rotation. Now, how do you do that? Okay, so maybe I should pause a little bit and ask for suggestions. If any one of you have a suggestion, let me just hear it. Any ideas?
So what if we consider the circle on the surface which will contain the point, the hole?
There are countably many holes, not one hole.
Yes, I mean for each circle,
Okay.
I mean we will
But I say
get
you have to do it using only two parts. If you do that, then for each circle you have to make two parts.
yes.
Just two parts, and that will cover all holes simultaneously. Yeah, you are right. We are going to use that same circle tree. No doubt about that. Okay, so I will give you a hint. The hint is this. Suppose this is the Earth, this is the globe, and the points are given in such a way that every point is in its own latitude. You remember the latitude? They are the horizontal cuts. If you consider the equator as the horizontal, so you cut parallel to them, that is the latitude. I used to get confused about what is latitude and what is longitude, so I reminded you, latitudes are the horizontal cuts. Now, if all these latitudes had been, all these holes are on the same latitude, uh, are on distinct latitudes, that is, no two holes are on the same latitude, then it is pretty easy. All that you do is you simultaneously apply the circle trick on all these latitudes separately. So for each latitude, you have to pick one particular angle, which is an irrational multiple of pi, and you will rotate the entire globe simultaneously. So all the latitudes will move simultaneously. No latitude will ever sit on top of another latitude because we will rotate it centered around the axis of the Earth. So latitudes will remain inside themselves. The only thing is that you have to make sure that all the holes are covered. So that's not a problem now, because for each one of them, you will rotate it by one radian. That's all. So you'll just simultaneously take all those points and move everything by one radian. So everything moves in its latitude by one radian, filling up the hole. The problem is what happens if more than one point land on the same latitude? Well, the answer is very easy, because after all, it is not the Earth. No one has given you the north-south axis. You are free to choose the axis. It's a sphere. You can turn it in any way you like. So look at all the possible circles that you get by joining any 2 points. So any two of these holes. So that will give you only countably many such circles. And how many possible positions are there for choosing your north-south axis? Obviously, uncountably infinitely many, because you take any point on the sphere, look at its diametrically opposite point, consider this as north pole and that as south pole, and you will get one possible axis. Out of these, you have to avoid only countably many of them, so that 2 points are lying on the same latitude. Again, the same story. You have uncountably many things to change from, only countably many things to avoid. You can still just find some way of choosing your north-south axis such that with respect to that, no 2 points land on the same latitude, and then just apply the circle rule. Which means if I give you any sphere with countable number of holes, you can always imagine an axis not passing through any of these points, such that you pick an angle such that no hole just gets into another, and simply rotate. So this is what I will call the countable hole strip. And this is step 2 of our proof of the Banach-Tarski theorem. So the first was the circle trick, and this is actually a corollary of the circle trick. If I give you a sphere with countably many holes, you can always cover them up out of thin air. Okay. Now we come to Hausdorff's paradox, which is kind of the stepping stone or the main argument that goes behind Banach-Tarski paradox. Again, Hausdorff's paradox should be called Hausdorff's theorem. It's a perfectly rigorous theorem, but I have never seen it called Hausdorff's theorem. Everyone calls it Hausdorff's paradox. And it says the following. So it is in the proof of this paradox that the main load of the proof of Banach-Tarski theorem will come. Hausdorff's paradox says the following. You start with a sphere. By a sphere, I mean only the outer skin, not the interior. If I take that, I will call it a ball. So I am talking about the sphere, just the shell. And you have to split it into finitely many non-overlapping parts. You rotate and refit to create 2 spheres identical to the original. So very much like the Banach-Tarski theorem, except that we are not working with solid balls, but with only thin sphere. And as a result, Hausdorff's paradox does not pack that punch, because we know that the volume of the sphere, just as the shell, is anyway just 0. So all that it shows is 0 plus 0 is equal to 0. It does not have that punch that 1 plus 1 equal to 1. 0 plus 0 equal to 0. Surprising in this particular context, but not really that, excitement. Okay, so let's look at the proof. And Banach-Tarski is just a stone's throw away from this. And the proof of this is pretty fun. I would like to draw your attention to the term finitely many. So there are only finitely many things. The argument uses infinity, but the actual thing that you do involves just finitely many non-overlapping parts, and the transformation is just a rigid body transformation, namely rotation. So I start the proof. The first concept here is the concept of an independent rotation pair. The independent rotation pair is like this. So if you have this sphere, you can rotate it in various ways. When I say rotate, I mean that you have to choose an axis and also a direction and magnitude of rotation. So I take an axis, rotate 30 degrees counterclockwise along that axis. When I look at the axis from this end or from that end, so something like that. That's the rotation. Now, by an independent rotation pair, I mean two rotations, A and B. So each rotation has its own axis and its own magnitude and direction, such that all possible combinations, like you first rotate by A, then by B, or first B, then A followed by A followed by B inverse. B inverse means the opposite thing of B. So all these things are distinct. If that is the case, I shall call these two rotations to form an independent rotation pair. As of now, I am not claiming that such pairs exist, but actually they do exist, a lot of them, uncountably infinitely many of them, and some of them are rather easy to construct. In fact, I can give you a rotation pair where the axes are very nice. I can take basically the x-axis and the y-axis as my thing. So A will possibly be along the x-axis, I mean centered around the x-axis, and B will be a rotation centered around the y-axis. I will leave the z-axis untouched. And I can create independent rotation pairs like this. So here is a point. So if I rotate, so I'm just showing the rotation. Suppose I start with that point and I give a rotation around the blue axis. So in that case, it just moves. You saw how it moves along the blue axis. Now, if I give it a rotation along the red axis, then I will move like this. So the A motion, that was the first motion, will take me along the blue circle. So when I apply A, everything will move parallel to that blue circle. And whenever I apply the red thing, that is B, I will move parallel to that red circle. And I can create everything in the A, B inverse, B inverse, A, B inverse, and all sorts of things. Any finite string of all these operations. Wherever I go, all these points will be distinct. You can see that this is basically a quick generalization of what we did for the circle trick. Here I said that I will take a rotation such that no point lands again on top of some earlier point. And there it was very easy. Just take an irrational multiple of pi. Here it is not that easy. That's why I need this concept of independent rotation. You keep on doing things, you are never going to land on your own tail. So naturally the question is, do they exist? Yes, there are many such pairs. And here is one very simple example. You just take this very famous Pythagorean triplet 3, 4, 5, and you consider the two angles, the blue angle and the red angle. Apply the blue angle along the centered around the x-axis and the blue centered around the red axis. They will constitute an independent rotation pair. The proof I am going to skip, but it needs nothing more than higher secondary level trigonometry. You just prove it using induction. You prove that after the n steps, the things are distinct. Then you show that at the n plus first step, the thing must be distinct. That is, if you apply any combination of these at most n times, the points are all distinct. You apply it one more time, then the points will remain distinct by induction. The proof is somewhat tedious. It uses the sin a plus b formula a number of times, but absolutely easy. So I am going to skip that. So just understand that there are such independent rotation pairs, and I shall pick any one such, say A, comma B. Now the set G of all possible rotations, that is countable, because these are nothing but all possible finite sequences that you can make out of A, B, A inverse, and B inverse. So the typical elements are just A itself, and you can also just do nothing. So doing nothing is also allowed. So A to the power 0. You can do B, you can do A inverse, B inverse, AB, BA, AA, BB, A inverse B, AB inverse, A, B inverse, B inverse, B inverse, A inverse, all sorts of things, all finite strings. These are all the possible rotations, and they are all distinct. Now, there are certain little problem, just a technical problem, is that I can write the same thing in a number of different ways. I can write A, or I can write it as AA followed by A inverse, where A and A inverse actually cancel each other out. So we just want to write everything in the reduced form. So whenever I will have A inverse side by side or B inverse B side by side, I will cancel. So I will always write this A, B, B inverse A as AA. And that will ensure that all these things have unique way of writing. So it is not that you take the same thing and just write it in a just some different fancy fashion. So I just remove that. It is somewhat like choosing the decimal expansion of numbers. We know there are certain numbers which have got multiple, which actually have got two distinct decimal representations. One is terminating and one is non-terminating, and we can just have the convention that we shall never use the terminating decimal expansion. In that case, everything has unique non-terminating decimal expansion. Just a technical thing so that we do not run aground in later steps of the proof. Okay. Using this, I am going to give you the most important concept, orbits and addresses. The idea is this. Suppose I start with one point, say the green point. I have shown you a point, the green point. Now I apply my, say, A move. I am showing A in blue. So I turn it by, so centered at, so turn it around the blue axis. So this green point moves to that first yellow point. Then I apply B, that is turn the red handle by that specified amount, and then the yellow point moves to the next yellow point. Then I again apply A, but in the reverse direction, that is A inverse. So I get the blue arrow after that. Now observe that this blue arrow is smaller than the earlier blue arrow. That is because I have now moved closer to the axis of rotation. So I am always moving by the same angle. As you come closer to the axis of rotation, you will have, sorry, that. So when I am doing this, so and then I'm moving closer to the axis of rotation, then the arc length will be smaller. And then possibly I apply B inverse, that is I take that red arrow in the reverse direction. So from one green point, I'm going to all these yellow points. If I take the set of all the points where I can move, I will call that the orbit of the green point. So by orbit of a point, I mean the set of all positions it can go to after the rotation. So I have that rotation set of all rotations G. Everything that I can do, I will have that orbit. And by the very way I constructed these things will all be, this set is of course a countable set because I have only countably many rotations that I have. So I will call this an orbit. Now you can easily understand that the different orbits must be disjoint, because if you can move from this to that, then obviously they will be just Because if two orbits share some common point, in that case, from this orbit you can come to the common point, and from the common point you can go to the different orbit. But in that case, that means from one orbit you can go to the other orbit. But if you can go from one point to another, they must be of the same orbit. So the different orbits must be disjoint. If you can go from one point to another point, they must be all in the same orbit. So essentially, by definition, the orbits are all disjoint. Now I do a little trick. Not a very great trick, it's a little trick. What I do is, I have so many orbits, right? And remember, the orbits cover everything, because for every point there is an orbit, and the total number of points on the sphere, that's uncountable. Size of an orbit is countable, so there are uncountably infinitely many orbits. What I do is, from each orbit, I pick one representative point, any arbitrary representative point. I just pick one, I give it a fancy term, I call it monitor of that orbit. Nothing very technical, I just created this name monitor. So for every orbit, I pick one representative. Now, once I do that, I have a name for that. I will call it a choice set, because I have chosen one point from each of the orbits. Okay, so now I can write down the address of any point. I will do it in this pair notation. So I will say, who is the monitor of each orbit, and how do you get from the monitor to that point? So it is somewhat like when you write down the address, you write down the name of, say you write down the zip code, and also you write down the exact house number. So the zip code takes you to one locality. Inside that locality, you can find out which particular house number the letter has to be sent. So the house numbers may be repeated from one zip code to another zip code. So house number 1 under this zip code is different from house number 1 under a different zip code. So the zip code sort of narrows it down to some extent, then the exact house number narrows it down further. Similarly, the monitor identifies the particular orbit, and the rotation identifies the exact element of the orbit with respect to that monitor. So let's take a simple example. Suppose I want to express the address of the first green point. Then I will say it is M, A. M is the monitor. Start from M, apply the rotation A. Wherever you go, that first yellow point, that is the address. Now, similarly, if I want to describe the second yellow point, it will be M, AB. Just observe my notation. I am writing left to right notation, not like a function composition. You first apply A, then you apply B. I am writing A first and B next, because that's how it's natural to read. So I use this notation. If I want to describe the next point, it will be same M, but A, B, A inverse, and the fourth point will be called A, B, A inverse, B inverse. In this way, every point has an address of the form one monitor element followed by one finite string of A, B, A inverse, and B inverse. So I want to address the points by their address. So the natural question is, are the addresses unique? Yes, except for the orbits of the axis endpoints. Now let's see why. I have shown here one point, which is at the end point of the axis. Now you can understand that if I apply rotation A to that point, that will have no effect, because it is sitting right on the axis of that A rotation. If you rotate, the axis does not move. So if you come up with some address, I can append any number of A after that, and still it will remain the same thing. So the address will not be unique. So whenever a point can land at some of these axis endpoints, then the address will not be unique, and it should not be very difficult to see that though these are the only points that will cause problem. Now, since we know that there are only countable number of points in an orbit, and we have to get rid of only 4 such orbits at most, because there are 4 endpoints of the 2 axes. So only countable number of points do not have unique address. So those are the pesky things. Everything else has got unique address. Again, much like decimal expansion, only countably many numbers do not have unique decimal expansion. Everybody else has unique decimal expansion. Like that. Okay. So now we are in the thick of the battle. What I will do is first I will get rid of those pesky points. So there are only countably many of them on the surface of the sphere. We know by the countable trick that we can always get rid of or bring back any countable number of points on the surface of a sphere. So forget about those. For the remaining things that have got unique address, I will split them up into 5 different parts. So I'm drawing something like a Venn diagram where all the points are shown by this rectangle. And at the very center sits the monitors, all the points that constitute the monitors. Now, every other thing has got an address. The monitor followed by an address. Of course, even the monitor things have an address. For them, that rotation part is just the identity rotation. Don't do anything. For everything else, you have an address. And I partitioned them into 4 parts. Everything that ends with an A, everything that ends with an A inverse, everything that ends with a B inverse, and everything that ends with a B. Because my address is nothing but a finite string of these 4 things, A inverse, B, or B inverse. So the string has to end with one of these 4 things. So I have just partitioned everything in this way. So when I say A dot 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 A, I mean the very last rotation applied is A because of my notation of reading from left to right. Now focus your attention on the first 2 parts, the things ending with A and the things ending with A inverse. I have just given you another copy of the same thing. I'm going to define a function. So this is my domain and that's my codomain. That's why I just made 2 copies. What I will do is I will leave all the points whose addresses end with A fixed. Just like that circle rotation thing, I left part of it fixed and the remaining part I rotated. Similarly, all the points which ends with A are left fixed. Now I will take a closer look at all the points that ends with A inverse. I am focusing my attention only on the A and A inverse part. All the other things I am forgetting for the time being. Take a closer look. All the things that ends with A inverse, what is the rotation that you applied just before that A inverse thing? The very end thing is A inverse. What did you do just before it? It could be another A inverse. In that case, it ends with A inverse, A inverse. It could be just nothing. A inverse is the very first rotation that you have applied. So it just is A inverse. It could be just the immediately preceding thing could be a B inverse, or the immediately preceding thing could be a B. As a result, that A inverse block gets partitioned into further 4 things. The A inverse cannot be immediately preceded by an A, because had that been the case, the A and A inverse would have cancelled each other out according to our convention. So it can be preceded by either A inverse or B inverse or B or nothing. Now what I will do is I will take this part and on top of it I will apply the A transformation, which will effectively cancel off the very last A inverse. So what happens? The part that ended with A inverse, A inverse, A inverse now has the last A inverse knocked off, and now it just ends with A inverse. The part that had A inverse and nothing before it gets that A inverse knocked off, and you get back some monitor point because you have no other rotation. The part which had ends with B inverse A inverse now ends with just B inverse because the A inverse has been knocked off. And similarly, the part which ended with B A inverse now ends with just B with the A inverse knocked off. So what is the effect that we get? The effect is we left the A part fixed and the A inverse part rotated. That same rotation gave rise to everything in A inverse, M, B inverse, and B. So, out of just the A and A inverse block, I have been able to reconstruct the entire sphere back again. And that is the surprise step. So this is the step. This is the reason why we are developing all this machinery. Now, there is nothing profound about A. Whatever you have done with A, you can as well do with B. I am not even touching that M thing. So, what's the upshot of all this? You see, I leave B unaltered and I apply the B inverse thing, I apply the rotation B. So the upshot is the following. Let's get back to our sphere and just call this trick the 5 parts trick, and this is the last trick that we are going to need. So this is what we did. So this is the proof of the full house dog. I start with the sphere. It's a hollow sphere. Step 1, I remove the points with non-unique addresses. Now here I have drawn it from an artist's perspective. Of course, the points with non-unique addresses, they are some orbits, so they are a countable dense set. I cannot really draw them like this, but I have just drawn it in a sort of picturesque way, as if there are certain holes here and there, but it is all over the place. I have removed the dense set from it, but it is just for a pictorial representation. I removed all the points with non-unique addresses, which means I created countably many holes. And then I consider this 5-part thing. The blue points are all my monitors. The green points are those points that have their address ending with A. Red things are addresses ending with A inverse. Yellow things have addresses with B inverse, and cyan things have addresses ending with B. So I have a very colorful ball with countably many holes, of course. And the points are all sort of mixed together. I have drawn them mixed, but in practice, they're even more mixed. You cannot really tell them apart. They're as mixed as rationals and irrationals. Now I focus my attention on these two things, the green and red part and the yellow and cyan part. What I do is, just in order to visualize, I will split it like this, as if I have taken the green and red part and set it aside. I have shown it to the right, so I have written the green and red to the left. Similarly, I take the yellow and cyan parts and set it aside, and the blue part, the set of all monitors, that is in between. Now, I have already told you I am going to keep the A part fixed, the green part fixed, and going to rotate the red thing by an amount A. So I rotate it by the red. As a result, I reconstruct the entire sphere. That's precisely what I mentioned. With, of course, those little gaps, the countably many holes that I left originally, those things are still not there. Because when I started, I did not even start with those things. So those things are still missing. Well, I will do the same thing with the other sphere. In this case, I will rotate the yellow part. And as a result, I will create another sphere with precisely the same countable holes, countably many holes. Those are precisely the points that are, excuse me, those are precisely the points that do not have unique address. But why do I care about those countably many points? Because I already know that countably many holes can always be rectified by my countable trick. So I will just do that thing. I will pick an axis such that none of them are on the same orbit, give a rotation, and so immediately I join them back. Of course, I am showing as if I am working with separate balls. Right? That is deliberate. So I started with one ball, and now merely by splitting it up into first 3 parts and then rotating, and finally I had to apply the countable trick, which means I had to split up further 2 parts. So that means I did the 2-part thing twice. So I have split it up in at most 5 parts. Just repeated, and I produced 2 spheres exactly identical, point by point. Nothing is left out, not a single point. Identical to the original sphere, and as a byproduct, I have left the blue sphere additional. You can throw that away. So I have not only produced two spheres, but some byproduct that you can throw away. I have produced something more than two. And that is the proof of Hausdorff paradox. Still, if you look at in terms of volume, I have proved that, well, 0 is equal to 0 plus 0 plus something, and that something is still 0 because I am working with only the thin shell. So really no mathematical volume contradiction, the thing that gives Banach-Tarski its punch. Now I will make it thicker. So earlier I worked with one-dimensional, thickened it into two-dimension. Now I will thicken two-dimension to go into three-dimension. So here is what we worked with. We worked with the shell. That is the thin shell I am showing. I have deliberately split it up into two parts so that you can see the interior. There is nothing inside. I am like a magician. I am showing, see, there is nothing inside. But we are going to make it thicker. And you can easily understand whatever I have done earlier, I can do the same thing here again. Earlier, I was working with points on the circumference, points on the surface. Now, I will just go deeper. For each point, I will also go deep into the shell. And whenever earlier I was moving points, I will now move that entire stick, that radially placed stick. So I can do the same thing with a thick shell. So give me a sphere with a thick shell, I can apply the same argument there and get it. Well, that now has started to give me the contradiction of volume. But I said I wanted to have a full ball, a solid ball. I still am leaving out a hollow. I can grow and grow and grow, but can I make it a complete sphere? Well, no. Because if you do that, there will be an overlap at the center. I want all my pieces to have no overlap. Here, I will have overlap exactly at one point. Because if I want to say, I will move I will move the green stick, but not the blue stick, then I am at a problem because the center point belongs to both the green stick as well as the blue stick. So do I move it or do I not move it? So that will be a problem. No problem. I will just remove that point at the center. So if I have the problem at the center point, remove it. Because I have that circle trick at the very first. I will just imagine a little circle over there. You have the point. Okay, apply the circle trick to vanish the point. Do the entire business. You will still get this solid ball with one point missing. Apply the circle trick back again and you will get back. How many pieces we have made? Five pieces. For this circle trick, add one more piece. Now you are splitting it up into 6 pieces. Okay, I said finitely many pieces. So 6 pieces are also allowed. So I can do it in this way. So now I have proved the entire Banach-Tarski paradox. I started with the entire ball. I removed the center point. Then I removed the countably infinitely many points with non-unique addresses, did that Hausdorff thing, put them back, brought back the countably many holes, and finally brought back the holes. Done. So what have I proved? I have proved that 1 is greater than equal to 2 because I started with the ball. Look at the volume of the ball. I split it up into 5 parts. Well, if you want, so in this case, I say 5 parts. If you want to be really specific, you'll possibly say, yeah, I will possibly say 6 parts. So volume of parts 1 and 2, that is equal to volume of parts 4 and 5. They constitute the entire ball. I have not written that other part because that's just a circle trick or just a countably many points trick. They will not contribute to the volume. So that's why it is correct actually. So volume of part 1 and 2, that is same as volume of the ball. Volume of parts 4 and 5 alone, that is same as volume of the ball because I just rotated it. By rotating, volume cannot change. Yet parts 1, 2, 3, 4, 5, they were all inside ball. So basically I have proved 1 is not just equal to 2 because I have thrown away that part 3. So maybe I have thrown away something extra. So 1 is actually greater than or equal to 2. And that means confusion. And all the steps here are actually Just impeccable, right? So I have shown 1 is greater than equal to 2. Now you might say, hey, we do not need all this work. We already know. So when we were children, we all did this thing. We have a similar paradox. You want to prove 1 is equal to 2, 2 is equal to 3. So this is how even a child can prove it. And this kind of puzzle you can see in many places. It says 2 minus 5 by 2 whole square is 3 minus 5 by 2 whole square. No one can possibly deny that. Take square root of both sides. So 2 minus 5 by 2 is 3 minus 5 by 2, and that is 2 equal to 3. So here also I have given you a paradox proving 2 equal to 3. But of course, we know that this is not correct because we have violated one thing, that therefore at the first of the second, at the at the start of the second step, that is not true. Squaring is not a one-to-one operation. You just cannot take square root, any square root, and ensure that just because squares are same, square roots are also same. So you are violating some rule of mathematics somewhere. The surprising fact with Banach-Tarski theorem is that when it was first proposed, according to the existing state of mathematics, it was not contradicting anything postulated in mathematics up to that time point. So it is a theorem. So that is the shocking news. So mathematicians now have to think that if so this really means based on whatever we have been working with, so whatever Gauss worked on, whatever all the great mathematicians worked on, there is somehow this argument lurking somewhere. You can basically prove that 1 is equal to 2 or 1 is greater than or equal to 2. This means there is something in these steps that we should ban. It is not yet banned. We should ban at least one of the steps. Otherwise, the entire edifice of mathematics is going to fall down. You can really prove that 1 is equal to 2, which means chaos. All the steps are correct according to our present state of knowledge at that time. So you have to declare, you have to censor at least one step. Now, which one do you censor? That is very difficult because the steps that we are using here have been used in many other arguments. So if you just suddenly point out one step and I say we are not going to use this step, that is difficult because that step may have been used in zillion other proofs. Those other proofs are going to collapse. So we have to find out something that is new in this argument, something that is so very harmless. It looks so very harmless that all through the centuries we have never thought that this is an Al-Qaeda guy. Now we have to remove it. Which one should we do? And here, the precept of Holmes to Watson is very, very appropriate. When Holmes said that, how often have I said to you that when you have eliminated the impossible, whatever remains, however improbable, must be the truth. So there is something which is very, very improbable in the argument, something that looks very harmless, but that is actually incorrect. So mathematicians set out to figure out those things. And they found not one, but two such arguments that are used in this proof, which are really suspicious, but they look absolutely harmless. Question number one. You said you pick 1 point from each of the odd bits and consider the set. Wait a second. Is M really a set? As I said, you'll be shocked. Why? A set is a collection of things, and these are some points. So what do you mean by really a set? It is a collection of points from the surface of the sphere. So what do you mean by really a set? Well, it's a question, and you can answer either by saying, no, it's not a set, or yes, it is a set. If you say that M is really not a set, then of course, life is very fine. You will say, in that case, the entire paradox collapses because the proof you said that it is a set. And I say M is not really a set. So your proof cannot proceed further. So if it is no, then you are happy. But if you say no, M should be a set, what's wrong with that? I have just picked up some points, one from each orbit, and put them together. That's a set. then the confusion continues. But then they say, no, there is another point where we can find a flaw. And that point is, you said volume. Because you say, all the things that we did, we are actually taking M and basically rotating things. So if I say M followed by A, this means I am taking M and rotating. So all the volumes, volume of part 1, part 2, etc., they are all obtained by volumes of M, because rotation does not change volume. So the question is, does M have a volume? Again, another of the weird question. Here is a set. Yes, the set should have a volume. Yes, it could be 0. That is not a problem. But does it have a volume? What do you mean by that? I'm not talking about whether the volume is 0 or non-zero. Whether volume of M is at all defined. Now, up to this point, people never heard this question. What do you mean by volume undefined? Here's a set, a bounded, nice set. What do you mean by undefined? But again, it's a question. So you can answer it either by no or by yes. If you say no, then again you are happy. You will say, well, your proof falls off. Because yes, I agree that you can split it into two walls. True, but you're going to talk about the volume thing because M does not have any volume. But if you again say yes here, then there is no other point that is new in this proof and you are stuck. Then you will get a contradiction and you will say impossible things happen in mathematics. You can't say that. As a result, there are two ways out of this paradox. Remember, it was a theorem, but once we put this condition, we put certain questions are no, now it ceases to be a theorem according to modern mathematics. Now we call it a paradox. Yes, you are violating some established rule, except that the rule was established after the theorem was proposed. The rule was motivated by this. Now, those mathematicians who say no at the first branch, they say we do not believe in axiom of choice. Remember, M was called the choice set. Now, this is not a place where I go into a detailed description of axiom of choice, but axiom of choice basically says that if I pick various elements from different sets and I put all these points together, do I call that a set? Axiom of choice says, yes, you can say that. Whenever you take 1 point each from a number of sets, you can put them together and that will be a set. There is a bunch of mathematicians who will not believe that. They said it will not be a set. If it is, you have to prove it. Now, those who take the other way around, they say, well, there are sets. Those are sets also. We do accept the axiom of choice, but there are certain sets that do not have any volume. Those are the so-called non-measurable sets. And most mathematicians in the world follow the second branch. They say, yes, we believe in axiom of choice, but we believe that there are certain sets which are so very weird, you cannot talk about volume or area or length or any kind of measure for them. And probability being one type of measure, we cannot talk about probability for them. That, of course, makes life quite difficult, and that is why we need that second thing in our probability space. Sigma algebra are precisely those things for which volume or probability can be defined. We are very careful not to go into these weird sets like our monitor set. Otherwise, we might land into absolute garbage. In order to avoid that, we put that as a safeguard, of course, making the life of beginning probabilities very difficult. Now, as I said, there are some mathematicians who will take the first branch. So, are there no contradictions? There must be one thing which is the correct way of doing things. Surprising fact, there is no correct way of doing things. Gödel proved in his famous theorem that both these worlds are perfectly consistent. So if you follow axiom of choice, in that case, you get one type of mathematics, and if you do not follow axiom of choice, you get another type of mathematics. If you do not follow axiom of choice, all your sets are measurable, but certain things are not sets at all. If you do follow axiom of choice, then there are certain things that are not measurable. So if you do not believe in axiom of choice, you can forget about sigma algebra. Everything has a probability. Everything has a so everything has a measure. Life is fun in that way, but life gets very complicated in some other way. So whether you use axiom of choice or you do not use axiom of choice, both will lead to independent and quite consistent branches of mathematics. Things that are true in this world will not be true in that world. Things that are true in that world will not be true in this world. There will never be any contradiction between them. No one can say this is the thing after some amount of discovery. This is correct and that is incorrect. No. He showed that it is never going to lead to any contradiction. So that's basically the end of the talk. However, that leaves us a gaping hole in our reasoning. So we started with this Banach-Tarski theorem. Out of the blue, we came across something which is horrible. We found that mathematics itself as a whole, there is something that we may assume or you may not assume, and both will lead to two types of mathematics. So how many types of mathematics are there? We just came across it by chance. Maybe there are some other things lurking out there. Well, yes. In his famous incompleteness theorem, Gödel said that there are uncountably, infinitely many such things lurking out there, for which no one can find the answer uniquely, like axiom of choice. Is it true or is it false? You can take either this way or you can take that way. You can never prove based on the existing knowledge. Have we found many of them yet? Well, axiom of choice is one that Gödel himself said actually proved that this way or that way both are valid. The other thing is continuum hypothesis. Gödel proved that one way is valid, and much later Paul Cohen proved that the other way is also valid. And for that single word, he got a Fields medal. So you understand how important this thing is. And Banach-Tarski paradox is just an accidental entry into this one. Okay, that's all. So the last slide only says, thank you for your patience. Thanks.
Thank you so much, sir, for this exciting talk. Like, just made our paradoxical concepts and ideas. I would request the members if they have any questions and opinions or ideas to share, and sir can address them. Would it be fine, sir? Hello.
Okay, no questions. That is usually always the case. There's hardly any questions. So you might just make some noise so that people who have fallen asleep will now get up.
Am I audible?
Yes,
Yes,
you are
yes.
audible to me. Yes, you are audible to me.
Thank you. I think I was not audible. So thank you for the talk, sir. Like, it made our paradoxical ideas and concepts made us more clear. If there are any questions, sir can address that. Like, would it be fine with you, sir,
Yes,
to address your questions?
if there are any questions, you can always reach out to me by my WhatsApp number. So I can just give my WhatsApp number to the chat box. Let me just see where is chat. It is 9231542600. So it is indeed difficult to ask a question after such a talk. It's a long argument, and I can share the slides because if you really want to go through it, I think you need to look at the slides once again.
Sir.
So I can share
Hello.
the slides. Right?
Hello, sir. Can you hear me?
Yeah. Yes, I can hear you.
Sir. Actually, it would be very helpful if you share your slides because we have planned that there are some members in our club who are still in their BSc. So we are planning that they will be making some explorations over our webinars, the topics, and they will publish it in as an article in our magazine, which we are planning to.
Okay.
So it and it was really very exciting. So thank you for the very unsung thing about
it. And I will just like to add as a note of encouragement to the organizers, I can see that there are only 9 people present here, including me. So the number might look like very small. So possibly only something like only say 3 or 4 people from outside other than the organizer. I will tell you that we regularly organize seminars, statistics seminars in our Indian Statistical Institute unit, in our unit, and we usually get something like 2 or 3 participants only. Okay, so only 2 or 3 audience size. You have got a much larger thing. So keep it up. Do not just give up hope. That number is so very small. It is much larger than what you get. Yeah.
So I want to
Sir,
add something to this. We have 8 people in this meeting just, but in YouTube we had more than like 30 people who watched.
Oh, you had more than 30 people. That's great.
Yes.
Okay, that's great.
So
That's
the
great.
great
Okay.
news.
Okay.
Sir, I had a question. It was
Okay, yeah.
you had mentioned Gödel's impossible theorem. Like he had, I mean, was that a theorem or was that a conjecture? I couldn't hear that. I mean, when he said that there were uncountable many possible uh,
Oh,
structures of
yeah, that is
mathematics.
a theorem. That is a theorem. That is a theorem. That is a theorem. That is a theorem.
So he had
Gödel's
proved that.
incompleteness theorem. Yes, prove that. That is one of the most celebrated theorems, if not the most celebrated theorem in mathematics.
I have a
Gödel,
request
yeah.
that in future, maybe it would be very nice if you give another talk on Gödel's incompleteness theorem in future.
That would be wonderful. That would be wonderful. But do you know Professor Sushimohan Srivastava? Sushimohan Srivastava, do you know him? SMS?
No, sir.
Okay, so he is the expert of this. So he has given this talk at very elementary level to undergraduate students, graduate students, and he is super enthusiastic about Gödel's incompleteness theorem, giving a nearly complete proof. So if you ask him, actually now he is a professor in the cultivation of science. He used to be a professor at ISI. If you want, I can introduce you to him. He will be more than happy to give that lecture. That will be exciting. Yeah.
Sir, I don't have any question, but I would like to just
Okay, I see you do not have any question, and also you do not have a good mic. So you should get a good microphone.
thank
Yeah.
you. The thing is that I would just like to just share a thing with you that just a couple of months ago, I and Shoham was actually doing a project of ours, and we were stuck in a thing that we were thinking that we will take 2 events, like we will classify 2 events such that one occurrence of one would imply the non-occurrence of other. Okay, so
Okay.
so we were trying to construct something like the probability of some event A given A or B occurs plus the complement of probability B given A or B occurs is something greater than 1 minus delta, where delta is a positive quantity. And while constructing that, we were stuck throughout the night because we couldn't make the sigma the probability of sigma 1. It was so obvious to us at the at the year of the dawn. We realized that it is we are doing what we are doing is just we are trying to apply Banach-Tarski paradox or something like that in a measurable set. So that was a thing. I would
Okay.
that's very funny. So thank you for your time today. We are very thankful for your support.
So you could follow the talk, right? In terms of my voice, in terms of the flow of the presentation, you could follow that, right? But the arguments are somewhat difficult, and you have to take more time to really go through it. I do not expect that you just